Hi, I'm Caleb, and I'm excited to present my team of Rohan, Zara, and Kirsan. We chose the Chevron track.
And the goal of this project is to predict peak oil rate given asset data. Information background and data significance. A major part of data science is understanding the data and variables we have, so we can use them as a basis to reach conclusions. It's easy to jump into the technical aspect of data science and overlook this key knowledge, so our team made it a point to seek out these crucial details. Luckily, the helpful Chevron mentors explained the variables we were given. On the left is a simplified graph explaining a few variables we have in our dataset in orange, and highlighting the oil recovery techniques within the pipe, and that's in blue.
Our initial approach would be first to visualize the data, then we would use one-hot encoding for feature engineering. We would pick out baseline models to predict oil rates. Some of the models that we'd pick out would be linear regression, random forest, XGBoost, and lasso. Finally, we would clean the data and feed it into these models. After executing the initial approach, shown on the right, we had a baseline model of roughly 96% using lasso regression. Regardless of this 96% model, our sample size was around 1,300, which is a major difference from 29,000. This disparity in sample size could potentially lead to overfitting issues, so we should deal with that.
So this is a graph of the number of NaN values for each column. In practice, we use these to figure out which columns had extreme null values, so we can drop them.
We used a correlation matrix in the form of a heat map to study the relationship between variables. To understand the most important features, we implemented random forest feature importance. We managed to drop outliers, we managed to drop insignificant columns, and we managed to impute data to fill in the empty values.
Now for our results and conclusion. By utilizing a combined technique of using visualizations to drop outliers, columns with especially large null values, and columns insignificant to peak oil rate prediction, and predicting and imputing the rest of the data, we achieved an RMSE of 83.6 with the cleaned initial given data using the random forest regression model. Although we obtained lower root mean square errors from dropping large amounts of null data, we settled for this method as our final RMSE. We concluded the models that resulted from dropping large amounts of data to produce a smaller RMSE were not reflected of the original dataset. As mentioned earlier, this practice could risk overfitting the model. So essentially, when analyzing the predictive accuracy of our models, we have to remember the nuances in the process of obtaining these results. This is why we used a combined approach of techniques to drop, fill, and handle the null values, which were the biggest challenge of the Chevron track.
The technologies used were Jupyter Notebook, scikit-learn, TensorFlow, GXBoost, NumPy/Pandas, VS Code, GitHub, TypeHigh, and StarkNet.
In a real-world situation, we might have access to get the null values filled in our model. This might help us increase our RMSE value and get better predictive accuracy score. Additionally, we might have increased our accuracy score if we were given more time, but since the time constraint of 37 hours, we did the most we could with the given time.
Thank you to the mentors, organizers, and competitors for this amazing journey and opportunity.